It's an absolute pleasure to be here. From a personal perspective, Astro 3D has done so much for my career, and I wouldn't be where I'm at today without Astro 3D. Um, Now, if there's anything on what I've learned about new tools, new methods, this is the message I got from Joe. Why do all the hard work if you can ask ChatGPT? So last night I put ChatGPT to the challenge of saying, hey, ChatGPT, what has Astro 3D done on the topic of mass and angular momentum? And it did a remarkable job. It picked up on all of the topics that I was going to talk about. Galaxy formation evolution, obviously, 3D mapping of the universe, integral field spectroscopy, even high resolution simulations, galaxy surveys, star formation, and feedback mechanisms. But the last one is the one I'm particularly proud of. The fact that ChatGPT already knows that we as a center are doing interdisciplinary research, collaboration across observations, theory, and computations is kind of a cool thing. So a shout out to everyone who's been doing press releases, putting their stuff online. ChatGPT knows about it, so the world knows about it. So I think this already is a legacy. So I guess that's my talk. That's all I needed to do. I'm just kidding, of course. There is a lot of work that has been done. And this is one of these beautiful ADS tools that you can use to say, hey, if I take all of the papers from Astro 3D, what are the network by authors? And so this is one of those where it shows all of the authors and all of the authors that are on each other's papers. And so this, to me, is a highlight of an amazing center. People collaborating across different themes, across different topics. And so when you look at these topics, you know, the ones that we've advertised and that we split the center in come out as these large things. And it's not that one is bigger than the other. They all sort of equally contribute. That said, I was asked to summarize mass and angular momentum, and that is an unbelievable amount of papers. It's 295 papers that are related to the topic of mass and angular momentum. So the challenge of trying to give an unbiased, complete overview is nearly impossible. So I apologize to everyone whose result I'm not going to be showing. It is going to be a challenge. I've picked the topics that sort of work with the flow of the talk that I want to give. I'll have my little soapbox moments where I'll just really give my opinion about certain things, but I'd really try to give sort of a nice overview throughout. But again, I can't be showing 295 slides. We would be sitting here until the end of the day. Okay, so let's get started. What is it that we actually promised as a center that we do? And so two things on this topic, on the origin of matter and the periodic table, stand out. It's how did structures in the universe grow out of matter, forming the building blocks of galaxies like our Milky Way? And then secondly, what forces have shaped the accumulation of motions of matter in the universe across space and time? So this is the topic of mass and angular momentum. Of course, this was subdivided, and these 5 points are going to be the thread throughout my talk. So these were the things that we wrote in a proposal, and I've summarized them here for you. And I've also added a little bit of a mystery one, because it would be kind of odd if we only did the work that we would promise we do. There's one key thing that I think stands out that I want to highlight throughout this talk. But the 5 points are to probe the most distant galaxies using gravitational lensing, to combine IFS on the AAT and 8 to 10 meter class telescopes with 3D data from ASCAP and other radio telescopes, to really utilize SAMI, which was already up and running at the beginning of the center, but to really measure and quantify mass and angular momentum in the nearby universe in the entire galaxy population. Also take advantage of the new instrument that was being built, so HECTOR. So HECTOR is a key part of our center, and the papers are going to come out soon. But I want to highlight the fact that, there's been a tremendous amount of work that was been enabled by ASTRO 3D for the HECTOR Galaxy Survey. Then there's a mystery that I'll leave for now. But the last thing is also to compare the Milky Way with extragalactic galaxies. So, of course, the Milky Way falls under the topic of mass and angular momentum. And I'd argue that it's probably the best studied galaxy. And we do this because we have so much detail, and in particular with the launch of Gaia in combination with extragalactic archaeological surveys, we're doing a tremendous job here. Okay, so let's begin at the beginning, mass and angular momentum. So this is a figure that I'll use a lot throughout the talk. Why? Because it shows both mass here on the horizontal axis and a version of angular momentum here vertically. So V over sigma is the ordered versus random rotation. But when we talk about mass, you can also split it into roughly two things. There's baryonic mass, composed of stars, both dead and alive, dust, cold gas, hot gas. But then there's the non-baryonic mass as well. So dark matter, both in the halo and also at a virialized halo mass. And perhaps there's even more mystery components that I'm not going to go into. But those are the two, that's the key thing in mass. So when you think about evolution of mass, there's various processes that can change the mass of a galaxy. You can have merging, where two galaxies come together and form a bigger galaxy. You can have star formation, which increases the mass. You can have gas accretion, but you can also remove you can also remove matter from galaxies. There can be gas outflows, which is particularly effective at the low mass end, but you can also strip material away during interactions. So these are the key processes that, we've tried to look into. What is the ratio? What is most important? And how do we measure these? When it comes to angular momentum, if you remember from your first year physics class, angular momentum is r cross m times v, but often we talk about specific angular momentum when we talk about galaxies, where you divide out the mass. And then it's just a simple cross term, r times v, that we use. That just looks at the rotation of your stars or of your gas. But if you want to go a step further, you can also look at the ratio of the ordered to random motions. So we measure v as the ordered rotation and the velocity dispersion of stars that are on more chaotic orbits. And then there is a third, which is very similar to V over sigma, but comes from the spin parameter proxy. And so this was a cosmological term used in particular for dark matter halos, but has been recast into an observational IFS quantity. And so lambda I, you'll see that a lot, is basically V over V plus sigma squared. Turns out it's very similar to V over sigma, so I'll interchangeably use V and sigma and lambda R throughout this talk. So what are the processes that can change the angular momentum or V over sigma within your galaxy? So the first thing that probably everyone thinks of is merging. We're all taught when two disk galaxies collide, you form a slow rotating elliptical galaxy. That's something that I'm going to be revisiting a lot. Turns out it's not that simple. But there's other processes. You can have stripping of material that tends to decrease V over sigma because you remove the outer disk part. You can have gas outflows, which tends to heat up your disk, so it lowers your V over sigma. But when you have star formation, when you're forming young stars in a very thin cold disk, you tend to increase V over sigma. And also when you have gas accreting to the outskirts, you tend to increase V over sigma. So all of these proxies, all of these measurements of angular momentum tell you something about the evolution of the galaxies. And of course, there are theoretical predictions. If you look at dark matter-only simulations and you measure the spin parameter of these dark matter halos, what you expect is a log normal distribution, either in V over sigma or a relation between your specific angular momentum and your mass that goes as a power law of 2 over 3. If you then just add your elliptical red and dead slow rotating galaxies, we're pretty much done, right? That's all we need to do. But is it really that simple? Probably not. We know there's a lot of diversity in the universe. When we look at the Hubble sequence, we see everything from spiral arms, bars, galaxies with larger central components up to ellipticals. So there's a lot of things happening in between these two regions that we'd like to understand. Just studying the quiescent population isn't going to help you, and this was done before Astro 3D with other surveys like with Atlas 3D, but with SAMI and HECTOR, we've really taken a step to look at the entire population. But at this point, you could argue, well, if I know a galaxy is a disk, I know it's rotating, and I can give a fairly good approximation of its angular momentum, and surely we can spot a disk from a billion light years away. So I'm going to play a little game, and I'm going to need everyone's interaction right here. This game involves standing up if you can. And so what I'm going to do is I'm going to show you a set of images. And when you're uncomfortable with that image not being a disk galaxy or disk dominated, you got to sit down. The goal is not to be the last person standing. The goal is to be like, where do you want to be in this comfortable? I will be looking at everyone and I will be judging you. So if everyone could stand up. So the first question, we're going to do an intro so that you get the gist of the game. This is a generational question. All the young people who are like, why are you showing the safe symbol on here? If you're uncomfortable with disk being a disk, you got to sit down. Okay, everyone got this one. Here's a fun one. Is this a disk? Well, this is actually a bulging disc. It's someone who had an injury. Sorry, I had to put in that joke in there. But the point is, of course, we're going to be talking about actual disk galaxies. So if you're uncomfortable with disk galaxy being disk dominated, please sit down. What about the sombrero? It's a very big bulge. Okay, everyone feels this is a disk. Awesome. How about this? We're still comfortable being a disk? This is incredible. By now, I usually have half of the crowd sitting down. What about this? Is this still a disk-dominated galaxy? Oh, yeah, okay. Okay, now, okay, good. I'm surprised by all of you. I love you. But what about this? Are we still talking about a disk-dominated galaxy? Wow, okay. Now, if by this point you're not sitting down, okay, awesome. So why am I playing this trick, right? Because for so long I've heard, surely, if it's a disk, you can see it rotating. The problem with disk, in particular when you go to lenticulars, if it's face on, you don't know whether you're looking at a massive elliptical or whether you're looking at a rotating disk. Sure, if you see spiral arms, you can be pretty certain that you have a disk-dominated galaxy. But here's the fun game. If you start doing bulge to disk decompositions, you would say that this galaxy is a bulge-dominated galaxy. So here's an analysis from Salo et al. Using Spitzer imaging. And when they do this bulge to disk decomposition on this galaxy, what you find is that this galaxy has a bulge fraction of 70%. That's not a disk-dominated galaxy. However, when you add a third component, so you say, what if this galaxy has a thick disk, a thin disk, and a bulge? The story is completely different. It's the same galaxy, it's the same data, but all of a sudden, that thin disk component becomes much more important. You have a thick disk of 21%, and now your bulge is only 30%. Awesome. Thank you. So you can add HST imaging, and then with the HST imaging, you actually see evidence for spiral arms in here. It's hard to see, but it is there. And the cool thing is, not coincidental. This is a galaxy that will be observed with geckos, so we are going to be doing the detailed dynamics on here. The problem with assuming that galaxies are just two-component becomes even more complicated when you add bars to galaxies. Because right here, you have two beautiful galaxies observed face on. We're all saying these are disk-dominated galaxies. When you do, again, your bulge to disk decompositions, what you find is that these things will mimic massive bulges that have large Sersic indexes, and you would again conclude that this is a bulge-dominated galaxy. So please be really, really careful when saying that structure equals morphology equals kinematics. All of this stuff is in the details. So this is work that I've been working on with Amelia Fraser-McElfie. And what I want to highlight here is there's three parameters shown here. So there's the bulge to total ratio, there is the Sersic index, and there's this lambda r parameter. Lambda r here low means that it's a slow rotator. If you're up here on the right, it means you're a fast rotator. Whilst a correlation exists between each of these parameters, there's a huge amount of scatter. For example, if I take a galaxy with a Sergic index of about 4, I can have a bulge to total ratio anywhere between 20% and 100%. If I have a bulge to total of 80%, I can have a lambda r that's either a slow rotator or a fast rotator. So the scatter in all of these correlations are large. So be careful with doing this. I'll get off my soapbox very soon, but I just want to make the point that, a lot of these language is taught in undergrad. And so then when we say we have spheroids and disks, we tend to think this is related to pressure and rotation support. This is correlated with red and blue, and this is correlated with old and young. And so all of a sudden you have spheroids that are pressure supported that are red and old, and you have disks that are rotationally supported blue and young. I don't think that's the case. Not all red and dead galaxies are pressure supported bulging and old. So be careful if you're generalizing these things too much. And to really drive home the point, if it walks like an orca, flies like a penguin, quacks like a husky, then how does it evolve? This is very much what I sometimes feel we're doing at conferences. We're generalizing things to make for a good story. But a lot of things are in the details. Okay, I'm going to get off my soapbox now. That was my very strong opinionated start of this talk. Let's talk about what this center has achieved. As I said, I'm going to be reviewing these 6 topics, and I'm actually not going to start with the first because Tanya is going to give an amazing talk about Agile. Agile is this brilliant survey where they used machine learning at the start to find all of these lensing candidates and then followed it up with spectroscopy to see if these are indeed lenses at high redshift. And the beauty of using lenses is that you can go to much higher redshift and still get both spatially resolved and magnified data on these high redshift galaxies. So you're using nature's magnifying glasses to study these high redshift population. So I'm not going to be talking about this. Tanya will do this. So I'm going to actually skip straight into the radio domain. Australia has a unique opportunity to really have a huge impact in this field. Radio is amazing for measuring angular momentum and also the mass of your gas, of course. And the reason for it is when you look at a radio galaxy and you look at H1, you go out to much larger radius than is possible with IFS instrumentation. Stars drop off very quickly in terms of the light profile, meaning that beyond one effective radius, which is usually between 2 to 10 kpcs, radio takes you out to that very large radius. And when you think about angular momentum, R cross V, being at large radius helps you tremendously. Angular momentum increases with radius, so you want to be at large radius. You want to be beyond basically where your rotation curve flattens out to get a good estimate of angular momentum. So here's a nice paper by Elagali using ASCAP Wallaby. This was published in 2019. Here's NGC 1566. Here's what you get for that velocity field. So it really extends massively beyond this stellar region. You get your velocity dispersion here on the middle, but this is typically how we show our data. This is a position velocity diagram. So velocity here on the vertical axis and position here. And then you see this beautiful arctan curve here that gives you your rotation. From this, you can measure angular momentum, and you can do this for a lot of galaxies simultaneously. This is, again, ASCAP Wallaby, and so the beauty is because you're combining all these different pointings in one single shot, so this is 2 pointings combined, but you're getting all of these phased array feed galaxies. So here is the Eridanus group. All of these dark blue points are galaxies. You get these observations pretty much in one go. So if you want to do large numbers of galaxies and you want to be doing this efficiently, get the angular momentum, ASCAP Wallaby, and ASCAP in general is your place to go. And as I said before, you can use this to test the theory of how angular momentum forms in a universe, how matter collapses. If you show your angular momentum here on the vertical axis as a function of stellar mass, you can measure the slope. And if you remember what the theoretical prediction was, it was 2/3. And so you can use this slope to distinguish between various formation models. Now, this doesn't line up exactly with the theoretical prediction. And the reason for it is that you have to be careful what type of galaxies you use in here. If your galaxy is purely rotation dominated, yes, angular momentum versus stellar mass will work well. If you start adding contamination from galaxies that have more central components, whether it's a thick disk or a slow rotating bulge in the center or a bar, you start to get a deviation. So here's beautiful work from on the left from Barbara Catanella using both X-gas but also SAMI H1, a follow-up of H1 for the SAMI Galaxy Survey. And you can measure things like the mass that's in H1 over the stellar mass as a function of your mass. And so you can use this to estimate how much gas is available that can be converted into stars at some point. But you can also use it again to study things like the specific angular momentum as a function of mass. And then here in particular, they find a slope which is shallower than the 2/3, shallower than the normal fall, and it's due to contamination coming into your sample. And I think the combination in particular of starting to using radio data, H1, angular momentum measurements in combination with IFS, so in this case here shown for SAMI, is the future. We have an immense community here studying the radio. We also have a large community studying IFS. These two are perfectly to be joined together. And this was one of the things, I think, one of the successes of the center is bringing together this expertise. And for me, the pinnacle here is, for example, the MOVE survey, where we have a large program accepted with ESO, one of the really big successes, designed to study not only the relation between H1CO and the stars, but also to study what happens to galaxies when they enter a cluster environment. Now, this has been done, of course. We've looked at galaxies falling into clusters, but it turns out high spatial resolution, looking at the really small scales within galaxies, is vitally important to do this. And so both Barbara and Luca have this large program looking at 40 Lie-type galaxies in Virgo to study how they quench and how they transform when they go into clusters. And I'll come back to this point later because how galaxies transform in cluster environments is still a big open question, and so that's why this is so important. So let's move on to IFS, in particular SAMI. As I said, SAMI was specifically written into ASTRO 3D because it was an ongoing survey, but we're only just beginning. And the reason why I'm saying we're only just beginning, by now, SAMI has published an immense amount of papers, more than 100 papers accepted, but 40 of these were enabled by ASTRO 3D. This was only possible of continued support for PhD students, postdocs, and people actively working on this survey. We've had 3 highly impactful data releases where we've used Data Central's team to release this data to the public to do more amazing science, enable others to join the collaboration by having access to our data. Now, the things that I'm going to highlight here, SAMI does, of course, a lot of amazing science. The things I'm going to highlight is quantifying what types of galaxies are in the population from a kinematic point of view. So we've heard about the Hubble sequence, we've heard about spiral galaxies, lenticulars, ellipticals, but what does it look like when you actually look at integral field spectroscopic data for these galaxies? Then I'm also talking about the impact of environment on the kinematics, and lastly, the role of quenching in galaxy transformation. And so here is basically all of the kinematic data that we have in this V over sigma diagram. So galaxies that are slowly rotating are here at the bottom, galaxies that are rapidly rotating here on the top, mass, low mass is here on the bottom left, high mass on the right. And the color coding here is using the Hubble sequence. So if you're blue, it means you're a disk, an SD. If you're here all the way at the bottom, you're an elliptical. Now, as I said, there is a correlation between these two properties. Morphology is a good first guess of your kinematics, but as you can see from these colors here, there's a large amount of overlap. Not all ellipticals are slow rotators. Only about 1/3 of these galaxies are what we call a classic slow rotator. So this is what we did. So we're using a wealth of data here. It's not just IFS. It's also using the best imaging data possible, and this is often overlooked. Having excellent photometry that accompanies your IFS is really important. And so we use that not only to derive the structural parameters such as your size, ellipticity, Sergic index, axis ratio, we also use the colors to estimate the stellar mass. You can do a better job from the stellar populations. You can use stellar population measurements to get the mean age, mean metallicity, the alpha enhancement, but also your stellar mass proxy. Then you can use your kinematics, and I'm just highlighting here your velocity and velocity dispersion, but you can also use high order moments to dive even further into the orbital distributions. And you can use this to estimate angular momentum, V over sigma, lambda r, whatever you prefer, and what is ever tailored to your specific science case. So one of the things that I did together with Sam, and this was really amazing work, pretty much enabled by Sam being an absolutely amazing person doing statistics, is let's have a look again at our population to see if there's actually statistical evidence for fast rotators and slow rotators. So what is shown here on the left is a diagram of all SAMI data showing lambda r versus stellar mass. And what we did, we used a Bayesian mixture model to ask the question, as a function of mass, is there any evidence for one or two populations? And so we used a beta function, either describing the low end, which is shown here in red, or the high end in lambda r in blue. And so the model didn't have a prior, just said, fit it as a function of mass, tell us what you think is the best solution. Then it turns out that, yes, indeed, there is a second population. It's very clearly visible here in this panel on the right for the most massive galaxies, where you see this giant peak of slow rotators. But you also see that there's overlap between two populations. So instead of saying this is 100% sure a slow rotator, we started talking about probabilistic slow rotators and probabilistic fast rotators. So for every galaxy, you get a probability of whether it's a fast or slow rotator. And then the cool thing is with that kind of terminology, but also with that kind of framework, you can do the exact same thing on simulations. And when I said ASTRO 3D is really enabled, things for me that I don't think could have worked otherwise, it enabled me to, and Sam, to use simulations, work with people like Claudia Lager, Charlotte Welker, but also external collaborators in Germany, so REA, to look at the simulations. In this case, Eagle, Horizon AGN, and Magneticum. And then the interesting thing is when you run that exact same method, you find very different results in all of these three simulations. Not all of them have very strong evidence for slow rotators, but the Bayesian mixture model still says, yes, there are two populations in every one of these simulations. The thing is, though, when you think about that classic picture of how a slow rotator is formed, when you merge two galaxies, you remove the angular momentum, why would this be different in different simulations? Why is this not a simple dark matter or particle test that you can do? So it turns out subgrid physics is important, even for kinematics. Even when you merge two big galaxies together, if you don't prevent star formation from happening, if you don't get rid of your gas, you are going to reform a disk and you will move away out of your slow rotator box. Now, one person I'll highlight here is Kate's work has been instrumental for all of this. She designed this beautiful code SimSpin, but also in this previous figure here, all of these data are corrected for seeing, which was only possible with the work that Kate has done. Again, the connection between simulations and observers was crucial here to really get the data going. Now, I've made this point before, but the classic picture of every elliptical is a slow rotator massive galaxy is just not true. And I think you need a large survey like SAMI, where you have enough statistics across the entire population to really measure this. And so this was beautiful work by Guo and the SAMI team, where they looked at the total mass function of galaxies, but then split by kinematic type. And so the three different colors that are shown here in cyan, you've got the fast rotators, the cold fast rotators, then you've got an intermediate class, which are your fast rotators minus, and then your slow rotators. The cool thing is that when you look at the fraction of galaxies as a function of mass, if you look at this bottom line here, this red line, these are your typical fast rotators. They only start to become important, not even dominate, but only become important at the high mass end. And similar work was done by Amelia Fraser-McElthey and Luca Cortese and the SAMI team, and they did a similar thing. They looked at the number density with dynamically cold disks, with lenticulars, and then also slow rotators, and looked where do they become important, but also where they're important in both the star-forming population and the quiescent population. What they find, and I'll highlight this figure here on the right, so number density is a function of mass. If you look at your slow rotators here on the right, again, only towards the massive M do they start to become more important. But in the general population, if you're thinking about a quenched galaxy, something that's no longer forming stars, we tend to think of ellipticals. Turns out, 35% of these galaxies are still cold rotating disks. So if we're thinking about what is it that we want to quench, well, the answer is probably we want to be quenching disks into disks, not quench a disk galaxy into an elliptical. So what about the impact of environment? Because this was one of these long-standing questions at Atlas 3D. Early types only found some evidence for it, meaning that when you go towards the center of a massive cluster, your galaxies are more likely to become slow rotators. So with SAMI, we revisited now using the entire population, having a complete sample. And what we found is that mass is really the most important parameter. And the reason why it's been so hard to find this trend before is that in order to become massive, you have to be in a dense environment. But if you're in a dense environment, you're very likely to be massive. If you're massive, you're also more likely to be a slow rotator. So all of these three are correlated, and it becomes a bit of a chicken and egg problem. So you really need to split the environment, and that's shown here on the vertical axis as the fifth nearest neighbor, as a function of stellar mass for all of these bins to do this independently and to investigate this. And when you do this, color coding is here such that your red are your slow rotators, and when you move towards blue, it becomes more of a fast rotator. When you do this, when you look at the entire population, you find that yes, indeed, in the densest environments, here on the top right, for your most massive galaxies, you are indeed likely to be a slow rotator. At fixed stellar mass, though, for the most massive end, the trend in environment is not that strong. It's only this regime here where you see a little bit of an effect. And so if you remove the slow rotators from the sample, which is done here on the right, you see that if for a Milky Way-like galaxy around here, environment plays a role, but so does mass. And so all of these trends are small. The change in kinematics that I'm showing here on the top right is about 0.1 in lambda RE out of 0 to 1. So it's only about a 10% effect. So you need a large sample, and you need to be really careful how you correct your data, in particular for seeing, because seeing impacts small galaxies more than large galaxies. Turns out early type galaxies tend to be smaller than late type galaxies for a mass like the Milky Way. So all of these effects come into play in these diagrams. But environment, yes, it plays a second order effect, but as we'll see, not in the traditional way. And so this is something that Scott will highlight. When you look at the same diagram, but now replace the kinematics by age, you find a very similar trend, meaning that when you go to your densest environments at the highest masses, you find that galaxies up here on the right, top right, are also your oldest galaxies. And so Scott has just published an immense paper really summarizing all of the SAMI results, I think, on this topic, where he shows that it's maybe not environment that's the key parameter, it's when you quenched. And so quenching is really important because what it does, it stops you from forming new stars in cold disks. And if you start out being very hot, so for example, in the early universe, things are very turbulent, you form a lot of disks, thick disks. If after that you stop forming stars, you remain a thick disk forever. If you also give a galaxy more time to evolve, it can also start to heat up its disk more and more, but it's not the interactions that are the dominant process here. It is the time you've had since you quenched that prevented you from pretty much building up a thin disk. And so this was already predicted by Claudia's work. So Claudia used Eagle. She did an amazing paper in 2017 and 2018 and already predicted this. So this was, again, one of those things where we've combined simulations and observations to really come to this result. As I said, if you're thinking about quenching, think really hard what you want to quench. So here's the favorite star formation rate versus stellar mass. Here's the star forming main sequence. And this is a paper where Amelia combined both SAMI and Menger and actually looked at, well, if you look in this diagram, if you look at all of your quiescent galaxies, what type of galaxies are these from a kinematic point of view? And then what she finds is that, well, actually, you find it only here on the massive end again do you find your typical slow rotators. Everything on the bottom left here are your rapid rotating disks. So how do you then quench a disk? And so one thing that Scott investigated, which is really cute, is actually saying, well, can I just take a disk galaxy that is full of forming stars, quench it, and then it fades. And when it fades, it will actually decrease in size because more and more of the luminosity, in particular, if you have a large central component which is older, more of the luminosity will go towards the center. And so you both decrease the size and you decrease your kinematics because of it. So when you take a simulation data, and so for example, if you focus on this point here, this is at age 0, and as the galaxy grows older, you start to see it going down in this diagram. So disk fading does impact your kinematics, meaning your observed kinematics. Internally, the stars haven't changed, but the way we observe it has changed. Unfortunately, it wasn't enough. So even though there's an effect of about 0.05 in lambda r, typically, when you compare this to the SAMI data, and that's shown now here in the points here in the middle, I don't think you can see my cursor anymore, but these black data points, what you see is that that's larger than what the simulation here predicts. So you need something beyond just disk fading to do this. Either it's more interactions, or it's the fact that your progenitors, again, so the galaxies that have quenched a long time ago, were dynamically hotter. And so I think SAMI has had an immense impact on our view of mass and angular momentum as a function of star formation rate, as a function of morphological type, as a function of environment. And so I think what we're finding now is that after stellar mass, which is the dominant parameter to change a galaxy's kinematic, environment still plays a role. But when you look at a galaxy like our Milky Way, it's not the interactions that count. It's the environment preventing you from building your cold disk further. Okay, so I did say there was, sorry, I'll just say we are continuing with this, of course. One of the things that was limited in SAMI was spectral resolution, sample size, but also aperture of your kinematics. And so with HECTOR, that has a better spectral resolution designed to do kinematics to much lower velocity dispersions, meaning to much lower mass, with a larger field of view so that you can really go out to large radius for these galaxies, increase sample size, but also higher signal to noise on your lowest mass galaxies. The diagram that we have for SAMI that I just showed you, where I'm showing environmental density as a function of stellar mass, these are all the galaxies we couldn't do with SAMI. Either because here on the bottom left, these gray points are limited in spectral resolution, or the points on the top right, which are limited by the aperture size. And this is not even the full HECTOR sample that we're going to do. This is just SAMI if we had the HECTOR instrument. So HECTOR will really blow this field out of the water. It will do an amazing job at looking even further into the various properties that we have. With 15,000 galaxies, you can do a lot more than what we had with SAMI, where for the kinematics, we only had about 1,800 galaxies. So stay tuned for HECTOR. Now, I had a mystery object in here. Does anyone want to have a guess at what this missing one might be? What is something that came out of the center on mass and angular momentum, going perhaps to slightly higher redshift that has had a huge impact? MACPI, thank you, the MACPI survey. So we've used VLT MUSE, another large program, to look at the galaxy transformation at higher redshift. And the reason why this was needed is that as beautiful HECTOR and SAMI and MANGA and all of these IFS surveys are, they only look at the local universe. And by local universe, I mean anything up to about 1.5 gigayears. I know MANGA goes up to 2 here, but realistically, I think we're about 1.5 gigayears in look-back time. Using the best instrumentation possible before the ELTs come online, there's this unique window where you can use IFS to still look at the kinematics with exactly the same spatial resolution and data quality that you have for SAMI and MANGA. And this was the MACPI. And this was a collaboration of the ASTRO 3D fellows that came together and said, how can we combine our expertise and submit something really amazing and wonderful that utilizes both our ESO membership, but also the fact that we're all working together here. And so this is MACPI. This is shown just for the stars. But I think one of the key things, the reasons why you need IFS is the combination of gas and stars. Stars behave relatively well, so you can do it with a single slit, but gas is turbulent, chaotic, so you really need an IFS to know where to look. And so one of the really cool things that came out I think it was just accepted either this week or last week, is this beautiful work by Kara Derken looking at the kinematics in a very similar way as we did with SAMI. And so when I saw this result, I was super stoked. Turns out these slow rotators, so galaxies that look like the stuff here on the left, this is now MUSE data at a redshift of 0.4. If you look at where, your population of slow rotators would lie in this bottom left regime, turns out the fraction is very similar to what we see in both SAMI and MANGA. So 4 billion years ago, slow rotators were already in place. So we have to look at higher redshift. And I think, as I said, if you're looking at stars, you can probably get away with using a single slit. And so people that have really worked on this that I want to highlight is work by Tanya, who did an amazing work here on stellar populations and looking not just at mass and size, but looking at the combination. So looking at potential of your galaxies. And then Francesco Eugenio also looked at this, combining not just legacy with low redshift data, but combining legacy, MACPI, and SAMI. And so these are really amazing works that are really pushing to what we can do without an ELT coming online. Okay, last topic. Initially, I wasn't sure if I was going to add the Milky Way to it, because Milky Way, we tend to think of beautiful individual stars. We can do chemistry, but we can also do kinematics. And we can do kinematics really, really well. And I'll show that in a second. And the reason why I'm so unbelievably stoked about every time I see this image from Gaia is because this is not a traditional image. This is not an all-sky image. This is taking the data from Gaia, taking every star that you have, and projecting it back onto an image. So this is a reconstructed image from individual data points that now shows all of the wealth that Gaia has to offer. And in particular, when you start to combine this with galactic archaeology, so Galar, Apogee, Lamost, we're driving, a new paradigm of what galaxies look like. The problem is, it's one galaxy, and I've asked all of you what your opinion is on whether a Milky Way is unique or not. So I'm just going to swap to this one here. Oh, come on, folks. This is... Okay, so the majority says, and this is a majority in the very smallest of percentage. Oh, that goes very quickly. Low number statistics. So most people say, yes, the Milky Way is unique because of property X, Y, and Z. Now, that meant, insert your favorite argument here. Now, for me, I'd say, yes, the Milky Way is a typical disk. So no, the Milky Way is not unique. That's my point of view. But it's also because I'd love to use the Milky Way as a template for understanding other galaxies. And it's going very rapidly. I love this. This is like election night. You don't want to go to bed until you see the final result. But I think what this shows is that there's both unique aspects to our Milky Way where we can learn something that doesn't exist in other galaxies, meaning spatial resolution, but also thinking of the Milky Way as your typical L-star, M-star galaxy, where all of the processes that we know about galaxy evolution occur. It's a pretty powerful galaxy to use as a template. And so this is the one thing that I want to highlight, and it's coming back. I think what we've learned from the Milky Way, and this is my very naive extragalactic takeaway, galaxies are very complex. And we're not using that complexity much when we're looking at extragalactic galaxies. For example, we're seeing in Gaia data, and this is work by Joss and by Thor, but also by Joanna, we're seeing all of these minor mergers bringing the disk into dynamics. We're seeing little impacts from 4 billion years ago. We're seeing traces of satellites and galaxies merging 8 billion years ago in all of this data. And it's amazing that we can do this. But it also shows that even though our Milky Way has been active in terms of minor mergers, major merger, the last one was probably 8 billion years ago. And so one of the cool things that I think the Milky Way can do is you can combine all of this data, you can combine your chemistry, you can combine your dynamics, and you can make a model of galaxy evolution that hopefully, we're not sure, but hopefully is applicable to all other galaxies with the same mass. And so this is a model by Sanjeev Sharma and Michael Hayden and the Galar team and other people, where they've looked at, can we explain this bimodality that we see in the solar neighborhood of alpha over iron? So these are your alpha elements, and then as a function of metallicity. And what you see in the Milky Way is that at fixed metallicity, you see this bimodal population. And the question is this just a generic feature of all disk galaxies, or was there a special event like a merger that came in that could explain this? And the beauty of Michael and Sanjeev's work is that they say, well, if you take our model, we can explain the entire data set from the center of the Milky Way to the large radius of disk, on the plane, off the plane, everywhere we can predict this. And what it takes is a good star formation history, chemical enrichment models that work, but also adding radial migration, meaning moving stars from the outer disk towards the inner disk and the inner disk towards the outer disk. So mixing of all these cell population. And one of the things that we got really excited about is that, well, we can actually maybe test this. And so this is where we're combining the extragalactic with the galactic, where we're saying, what if we were to observe galaxies in the same way? A complication is that when you look at where Gaia DR2 is with the radial velocities, we're looking in the solar neighborhood, which is great, but it's nowhere near to where we measure things with IFS surveys. There's a huge disconnect between the part of the galaxy that we're looking at for our Milky Way as compared to extragalactic. So if you want to do this, you need data going out to much larger radius. And so Nick and I did a pilot study on UGC 10738, galaxy that is very similar mass, is very similar morphology, but observed edge-on. And the beauty of observing galaxies edge-on is that you can separate the thin disk and the thick disk just by looking at where you are on your detector. You don't have to do anything fancy other than just integrate for a very long time. But when you do that and you measure your star formation history, you measure your mean metallicity, your ages, and your alpha enhancements, you can compare this directly now to the Milky Way. And so here it's really the combination of using these theoretical predictions from the Galar team that we did, that is shown on the left for the Milky Way, where we're showing the scale height as a function of radius, data color-coded by a metallicity, on the left the Milky Way, on the right what we got for UGC 10738. And you're seeing that roughly, not perfectly, we're getting the same trends, low metallicity in the outskirts, high metallicity in your thin disk. You're seeing the same with age. When you go into your thin disk, where all of your young stars are, so here on the bottom right, you see a young population, your older population sits here. And then lastly, the alpha enhancement, we also see the same thing, meaning that if you're in your thin disk, you're seeing low alpha. If you're going off the plane of the disk into your thick disk, you're seeing that same alpha enhanced disk. Does this mean that there is a chemical bimodality? No, not really. It's a little bit more complicated than that. But is this the first detection of an alpha-rich disk in a Milky Way analog? Yes, it is. And so this inspired us to go bigger and larger and deeper. And this is really the last thing I want to mention, and it's geckos. Geckos, again, for me, is the combination of all of the amazing things that ASTRO 3D had to offer. The conversation about, doing all of these things came after a talk when Deanne came up to me and said, hey, edge-on galaxies are pretty cool for starbursts as well. You can measure outflows. Should we combine efforts? And we said, yeah, absolutely. Let's do this. And so we came up with a sample that isn't just Milky Way analogs. It's Milky Way-like galaxies, meaning edge-on galaxies that may or may not have a bar, that are similar mass as the Milky Way, but then have a large range in star formation rates to really trace both a different star formation history, but also a different assembly history. Because you can only get a starburst in a recent universe if you had a recent interaction, whereas if you look at your lenticulars, so here on the bottom right, these things have probably been quiescent for a very long time. So by having a range of all these objects, you can do an immense amount of science. And this is one of the amazing things that you can do when you collaborate with people that study emission lines. Now, I'd say that ASTRO 3D has done a tremendous job at bringing together all of these different surveys. And we're not there yet. There's still a lot of open questions. There's still so much to do. And the amount of data is only growing. The future is really bright. We have all of these surveys that we're either working on now or upcoming instruments like MAVIS, which will really revolutionize the spatial sampling that we can do on these galaxies with the VLT. We have the full SKA coming. We have GMTs. We have JDBST, which is coming, LSST, Foremost, HECTOR. We're going to be drowning in data, but it's going to be a really nice death if we're drowning by having too much. This is all I wanted to say. I think ASTRO 3D has answered all of these questions and more. We have looked at massive galaxies in the high redshift universe using lensing. We have combined SAMI with ASCAP, with MUSE surveys. SAMI has had a huge impact. HECTOR will enable so much more science. MACPI was this beautiful outcome by the fellows. And lastly, I think we've done a tremendous job at making sure that whatever we do in the Milky Way is projected outwards to other galaxies as well. There were a lot of things I didn't say. There's topics on massive quiescent galaxies, dusts, CGM, duvet, tidal streams, ultra-diffuse galaxies, ancient spiral galaxies, shark, so many analysis tools that I didn't highlight. Amazing job, everyone. I couldn't mention all of this, but this is where I'd like to end. Thank you.
That's great. Thank you. Yes, sir. Questions? I will maybe try to go for students first.
Hey, yes, sir. Great talk. Really enjoyed it. I was quite interested in some of the plots you were showing with lambda RE and environment and mass and stuff. And I was just wondering particularly about the RE aspect of it, because we're only characterizing sort of the dynamics within one effective radius. And I was wondering what you would think the impact would be as we get onto these new instruments and we start to see get better resolved kinematics further out. Will we start to see like more pronounced environmental trends, for example, or things like that as we really explore the full scales of the galaxies?
Yeah, amazing question. Thank you. I think somewhat related to the work that you're doing, if you think about where in particular minor mergers and galaxy interactions have an impact, it's usually not the center of the galaxy. It's usually in the outskirts, in the disks. And so when you see galaxies interacting, you often see these long tails. With SAMI, we're not tracing those. And so work by, for example, Tom Rutherford, looking at galaxies with tidal features and without, we didn't find an impact on the kinematics. And that's probably because everything that's close to the center is deep within a gravitational well, is very hard to get out of. And so I'm super looking forward to looking at the larger radius to see if we see the more subtle trends. I think what the work has highlighted, though, is that the impact is probably going to be small. And so environmental impact in terms of what we've seen with SAMI within 1RE is about on the order of 10%. I don't know if it's going to be similar or bigger when you're looking at the outskirts. You're also looking at fainter stars, but it's probably going to be hard to detect. But I think this is where the new instrumentation is coming in. Things like MAC-Pi is already doing this. They can go out to larger radius because the data is a little bit deeper. Manga has a good radius as well, but HECTOR will really blow this out of the water. Because the key thing is when you go out to large radius, your velocity dispersion drops. And so doing all of these measurements becomes much, much harder. And so you need spectral resolution in order to do that. So that was one of the key science cases why I think HECTOR is the unique instrument to do this. Low mass and cold disks.
Thanks, yes, sir.
Thanks, man. Other questions? Darren. Oh, yeah. Oh, good.
Thank you. Very nice talk. You stressed many times at the start the fact that about 1/3 of the galaxies that are passive are disk dominated. And I was wondering if this is like consistent with a model for which like a galaxy undergoes like a starburst, then a quiescent phase, and then a starburst again. So for example, maybe these galaxies that we're seeing quiet now, they might form stars later on, or if those are just dead galaxies with no chance of forming stars ever again.
Yeah, that's a really good question. So what happens when you have really big starbursting events? And I think, one of the things that Barbara was showing earlier this week, we think about MH2, massive starbursting galaxy, all of these outflows. I'd argue it's still very much a disk. If you go towards lower mass, of course, all of these outflows can heat up your disk. And this is one of the reasons why when you go to low mass, you see your V over sigma dropping, something that we're seeing hints of in stars, but maybe don't have the spectral resolution and the image quality, something that HECTOR will change. I think in all of these starbursting events, unless you go to really low mass, it's really hard to get rid of that disk altogether. So I think it will change V over sigma as you look through history of these galaxies. I don't think it will remove this galaxy looking like a disk.
Okay, thank you very much.
Great, thanks. I think Darren next, maybe.
Oh, tell you what, no, I'll go.
So wonderful talk, and I always love the discussion about, is the Milky Way a typical spiral, L-star spiral galaxy? So in 2011 with Simon Much, we published a paper called The Midlife Crisis of the Milky Way. And so we were asking exactly this question. So the question was, if we were an alien civilization, a billion light years away building a galaxy survey of our local neighborhood, and we got a large population of galaxies. How would a PhD student there in that alien civilization classify the Milky Way, and would they call it a typical galaxy? And so our lever was the color magnitude diagram. And we wanted to ask, where does the Milky Way and M31 on the color magnitude diagram? And it turns out that the Milky Way probably, M31 definitely, is in the Green Valley. And so then the question becomes, is a Green Valley L-star spiral galaxy a typical, good template for characteristic L-star spiral? And so I might argue, no, it's not. But then I guess it depends on the science question you're asking. So I was wondering if you had any thoughts on that in terms of your opinion that it is, and how we rectify these sorts of different ways to look at the same galaxy.
Amazing question. Thanks for highlighting the paper. I mean, it's a lovely piece of work. It's one of the inspirations actually for the work that Susie Tunzipong is doing. She'll be giving a talk, I forgot if it's today or tomorrow, but tomorrow on this topic. And so one of the cool things is that what you call a Milky Way analog, as you said, depends on your definition. And so I think it was Ken Freeman who said to me, is like, well, if you use all of the parameters available and you end up with exactly a perfect Milky Way analog, then what's the point? Because we already have one. It's the Milky Way. So for me, it's the variety and all of the different parameters where you can say, what if I select a galaxy based on mass and color? What do the other properties look like? Can I find, something that with the same mass that is disky and has the same color, for example, in different environments? What do the kinematics look like? And so this is something that Susie has explored. Susie has looked at all of the variations of, star formation rate, mass, Boltzmann total, and just ask the question, how much variation is there? What type of galaxies do we pick up? What do the kinematics look like? And so I think it's taken the work that you've done probably to the next level by saying, like, what happens to all of these selection criteria? And I think other work that's been in the literature has said as well, is like, it's very hard to find a perfect Milky Way analog. And so maybe that isn't the right question to ask. And so I think this is why geckos, we didn't say these are analogs, they're just the same mass and have a disk. And then I think you can learn something new about star formation history and the star formation, the assembly history of these galaxies.
Thanks. Mary, and then Lister.
Well, back in 2001, I wrote it. No, just kidding. Sorry, I couldn't resist. So a couple of questions. One is, have you looked at a correlation with gas mass or total baryonic mass versus rotation? I would think one of those, gas mass in particular, I would expect to be tighter, but I'm not sure what would happen with baryonic. And also, is there a cutoff that you ran into where it does not work? Because I would expect that as you go to the low mass galaxies, that could be the case.
So this was partly, I'd say some of this was explored in Barbara Caranella's work using Arecibo on the SAMI galaxy survey to look at these properties. And so she looked, for example, at the Tully-Fisher relation, and then looked at the gas fraction to see how much of that could cause, how much of the scatter came from different gas fractions. I forgot what the key conclusion was, but there's been a few papers on this. So both X-gas and SAMI H1, the work by Barbara, has looked into a lot of this. And so typically, I think we tend to go, I think Barbara's work for the gas goes down to about 10 to the 9, which is also around the region where we stop trusting the stellar kinematic measurements because of the spectral resolution signal to noise. So that's sort of the mass regime, 10 to the 9 to 10 to 11, 10 to the 12, I think that we have coverage over. Thank you.
Okay, I think Lister.
Yeah, wonderful to see these plots of mass against environmental metrics for SAMI, and the exciting prospects for HECTOR, particularly going down to low masses. But could you say something perhaps in a more cosmological context about volume corrections and selection effects, and just how that would translate to a cosmological metric such as a velocity function or angular momentum function?
Yeah, so thanks for that question. So I think one of the amazing things that we've had for SAMI is that it was all selected from the gamma surveys plus the additional cluster regions. And so one of the amazing things that we have, of course, with gamma is extremely high spectroscopic completeness, meaning when we study environment, we know down to very low masses how big a group and how many members it has. In terms of what volume we trace. So in Julia's paper from 2015, it's very clearly said these are the different selection boxes that we do. And so as a function of redshift versus stellar mass, we take these different volumes to make sure that we're mass limited, meaning the way we're mass complete. And so all of the papers that I've showed, so the papers from Amelia, but also the papers from Guo, they have been volume corrected. So they have taken into account all of these effects. When I'm showing, for example, the mass and environment trends for the stellar kinematics, even though the overview smooth plots didn't have that correction in there, when we do our medians, we again correct for all of these things. The same thing will be done for HECTOR. So HECTOR is at the moment not just doing IFS, but it's also doing a deep spectroscopic campaign to get the completeness that we need from a spectroscopic so that we know what we're selecting. But in particular, we're using the proposed waves regions to take our targets so that when we get our 15,000 galaxies, we'll again have the deep spectroscopy to correct for good completeness, but also look at a larger volume. The only problem, of course, is that we are still looking at relatively small patches on the sky. For example, between the 3 and 4 gamma fields, we do see cosmic variation occurring. And so that's one thing that you always end up with. You have to compare it to larger surveys. But I think this is where Foremost and Waves and 4HS will do a tremendous job. I hope I answered your question.